My name is Mike Houston, and I'm the moderator for this event. I teach algebra and calculus near Pittsburgh, where I use TI technology to make tough-to-teach, tough-to-learn concepts accessible to all my students. Tonight, I'm excited to be joined by our two panelists, Michelle Reinhardt and Tony Norrell. Michelle has taught high school math and science at rural districts in Texas, while also working as a math and science consultant throughout the state. Her interests include technology integration, conceptual understanding, and curriculum and instruction. Michelle has recently been accepted into the Doctor of Education Leadership Program at the Harvard Graduate School of Education, where she will begin her studies this fall. Michelle, thanks so much for joining us. And Tony has over 25 years of teaching experience from 5th grade all the way up to college algebra, and worked with teachers as a math specialist at a regional education service center in Texas. She is currently an independent math consultant and a T-Cubed regional instructor. She enjoys writing and delivering professional development in both math and coding. Tony won a Presidential Award for Excellence in Mathematics and Science Teaching in 2007. Tony, so great to have you with us tonight.
Thanks, Mike. I'm glad to be here.
We're expecting a large crowd, so your audio is muted. Feel free at any time to send any questions to Michelle or Tony using the Q&A window on the right side of your screen. We'll also be using the chat window to send general messages. As a reminder, the session is being recorded, and we'll provide a link to the event certificate of attendance at the conclusion of the webinar. We hope you don't have any audio issues, but in the event that you do, try selecting Communicate from the very top of the WebEx menu and choose Audio Broadcast. At this point, Michelle is going to discuss our agenda.
Thanks, Mike. So here's what we're going to look at and kind of move through this evening. Mike's taking us through the welcome and introductions. Then we're going to look at an activity called Move the Cone, where we'll explore different drive commands for the rover and how this connects to other mathematics. We'll have some geometry applications in there, also some coordinate grid applications. Then we're going to kind of pivot and go a different direction and look at an application activity called Corralling the Sheep, where we'll use linear functions with restricted domains to control the rover's movement. And throughout this webinar, we'll be talking about how this work supports the math process standards and also math content standards in our respective areas. And then we'll also reflect and extend these ideas into other math topics as well. Stick around till the end of the webinar because there's going to be a drawing at the end for a free registration, I think, Mike, to a summer workshop. Is that correct?
That is correct. Thanks so much.
Yeah, no problem.
And Tony is going to discuss our expected outcomes.
Thanks, Mike. So our outcomes are that I can collaborate, think creatively, and solve problems while also exploring and extending mathematical topics. I can explore ready-made activities for learning mathematics with a TI-Innovator Rover, and I can analyze how computational thinking supports mathematical process standards.
Tony, thanks so much. Michelle, you have control. Feel free to share your screen.
Thanks, Mike. Okay, so welcome everyone. So glad you're here. Just a couple things to kind of get us started while you're maybe getting your or getting all set up. Make sure you have the chat showing on the right-hand side of your screen. I won't be in the chat much tonight, but I think Tony and Mike will both be there. So feel free to ask lots of questions, interact with each other throughout the session. Definitely a valuable way to learn from the experience. So Tony and I have been working with the rover for a couple years now and thinking about how can we really leverage the power of the rover in the math classroom. And so creating a webinar around that idea was like a really interesting challenge. We've done a lot of professional development and also professional learning of our own around how to do this kind of work, but all of that's really been face-to-face. And so tonight we're going to try to kind of in this digital way go back and forth between interacting with the coding side of Rover on the calculator and sharing with you some videos of what that actually would look like physically with the Rover. So that's just a little bit of overview about that. And then I'd also invite you to not worry about following along on your handheld calculators as we go. We're going to be using both platforms, both 84 and Nspire throughout the webinar. You'll be able to do anything that we do on both of those platforms. But don't worry about kind of following along in the minute with the coding. You can always go back and watch the recording later. Tony, anything to add to that before we jump in?
Yes, thank you, Michelle. I was going to add that the files, I think Mike will have the files available, so any of the activities that we're using, those files will also be available to participants.
Awesome. Yes, thank you for that reminder. So stick around to the end for those as well. Oh, and then one other conversation, Tony, I know you and I have talked about this a ton over the last year, is how do we specifically use the Rover to explore and extend and apply mathematics? So how do we really center the mathematics within this work and not necessarily center the coding? And that's not to say that the coding isn't important, of course it is, but how can we specifically use this as a tool for mathematical inquiry and application? And sometimes that will involve coding and sometimes it won't. And so we'll kind of be navigating that with y'all tonight and sharing some different thoughts about that as well. Tony, anything else before we jump into our first activity?
I think that'll do it, Michelle. The activities we're doing tonight, though, are part of a larger workshop that's also going to be available this summer.
Oh yeah, that's right. That's kind of some of the work we've been working on, and we'll share specifically about that at the end of the webinar as well, where you can find out about those, if there's a workshop like that near you, etc. Yeah, thank you for that.
Sounds great.
Awesome. So we're going to start, in a few minutes, we're going to get into an activity called Move the Cone. But first, we really want to kind of begin at the beginning, right? Like, what if I have a Rover set up, or I get my hands on a Rover set up, and I'm wanting to, like, write some programs and do some kind of introductory things with that? How do I even get started? So for this first part, we're going to be coding on the Nspire platform. But again, you could do this on either Nspire or 84 plus CE platforms. So we're going to get started on Nspire by just kind of creating a brand new document. And once we create a brand new document, we're going to go down to option number 9, add a program editor, and add a new program editor. So this is how we would write or how we would start to write a program on the Nspire platform. So I'll select New. It's going to ask us to title or name our program. Let's maybe call this one Drive 1. I'll push Tab down and press OK in order to name this program. So we've just set up kind of an empty program called Drive 1 on the Nspire platform. And so we're really looking at Rover specifically today. And so we're going to think about, okay, so say I have this calculator connected physically to my Rover. What are some of the different commands I can use to drive Rover around? What are the different things I could maybe do with that? But first, and I always have to remind myself to do this because I get so excited and I just want to get started. First, we actually have to connect the Rover digitally to the calculator as well. So they might physically be connected right now, but we also need to do a digital connection. So we're going to go to the menu and then down to the hub. And the Innovator Hub is a go-between between the calculator and the Rover. So I like to think we go through the hub menu to the Rover submenu. And then within that, we're going to send a message that connects the Rover. So I'm going to insert this line of code to digitally connect my Rover to the calculator as well.
So Michelle, I'm thinking that anytime I write a program for Rover, that needs to be my first line of code. Is that correct? Yes, and that's a lesson we have perhaps learned the hard way, right? That we've just like jumped right into, we want to do this, this, and this, and then we try to run our program and it doesn't work. So yes, we try to always kind of slow down a little bit at the beginning and remember to include that send connect. Yes, awesome, thank you.
Okay, so then from there, we're going to learn about or just explore some different drive commands. So I'm going to go back into the menu, through the hub to get to the rover. And then once I'm in this rover submenu, I've got all these different options, but we're going to spend time tonight looking at the drive RV or the drive commands for rover. And so I'm just going to have this little sub menu pulled up over here. Within the drive RV menu, there's all these different options. So kind of look down that list, and that might kind of plant some seeds for you about some different ways that you can drive or maneuver rover around. And so to explore these, I'm just going to pick some of them and insert them. So I'm going to insert like a forward command, and I'm going to put maybe a 4 after that. I'm going to insert, go through the hub to the rover. Let's get another drive command. Maybe this time we'll go left, I don't know, 90. Let me go, I'll get a couple more, y'all. We'll just put a couple in, and then we'll step out of it and think about like what would this do? So I don't know, maybe backward 2, and then let me get one more. So again, through the hub to the rover, go into the drive commands, and this time let's go right, I don't know, 45. So I'm going to pause here for a second and just kind of look at, we know what this first command does, the connect RV connects those digitally, the rover and the calculator. And I'd like you to think about what path would the rover kind of trace out or draw out if we ran this program right now. So if you have something nearby that you can write with and draw on, just kind of take a minute and kind of sketch out, what do you think rover's path would look like if we ran this program? So just kind of sketch that out for yourself. Tony, anything to add to that before we look at what that looks like when we run it?
No, I'm anxious to see what this is because I think I know what the 90 and the 45 are, but I'm curious about the 4 and the 2. So I want to see if my prediction is correct. Okay,
awesome. So when we're ready to run this, I'm going to model how we would run this, but again, you can't see my rover or anything like that, so you can't see mine run live, but we have a fix for that in a second. If I was going to run this, I would go into the menu, go down to check syntax and store, and then there's a run command right here. And you'll notice that there's also the shortcut, pull it together, sorry, Control R. We could also push Control R to run the program automatically. So I'm going to use that run command. It'll insert a calculator page, pull up the program ready to run, and then I'll push enter, and then my rover would run if my calculator is connected to it and you could see it. So that's just a little bit about how to actually execute that program. So from here, we're going to jump over to the slide deck, and in this we have Tony was a total trooper and captured video of all these programs in advance. So here's the program we just coded out, and then here's a little video clip showing what that looks like. And I think Mike's going to copy a link to this in the chat as well. Oops. So that if you have any trouble watching it live here on my screen, you can also just click that link and watch it live in the drive. I'm going to run this a couple times, but I invite you to think about, does this confirm your prediction? How does your prediction kind of compare to this? And then also maybe think about Tony's question. Like Tony's like, I feel like I kind of know what the 90 and 45 are or would do, but what's that 4 and what's that 2? Okay, and this is a meter stick over here. This is maybe like a 10 centimeter, 20 centimeters, 30, 40, 50, kind of just for a scale there or whatnot. So yeah, feel free to share in the chat like how what we're seeing here like confirms your prediction, that's what you thought it would do, or refines your prediction. And then maybe like what do you think those 2 and like what does the 4 mean? What does the 2 kind of mean? I'm going to jump back over to the code for a second. Whoops.
So, Michelle, I think my predictions on the 90 and the 45 were correct because I think those are in degrees.
Yes, ma'am.
Because it looked like it turned left 90 degrees and then it turned right 45 degrees.
Yes, ma'am.
I think Ellen said that it's moving in centimeters.
Okay.
And
so it's moving forward 4 centimeters? Sorry, Tony, is that what you meant?
Yes. I think so. She's just looking at it thinking, I think that it's in metric measurements, and I agree with that. Although the 4 did go a pretty good distance.
And it's kind of hard to tell because you can't really see the scale, but like from the edge of the ruler where my mouse is, that's 1 centimeter right there. Again, it's kind of hard to tell. So this is about 5 centimeters. This is about 10 centimeters, 20 centimeters, 30 centimeters, 40 centimeters, 50 centimeters. Do you know what I mean? Yeah, so one of the things that we begin to see, and again, like if we're really exploring this live, you would really get to play around with this and try what if it was like 0.5 or 10 or, what happens with those different things. So Ellen, you're exactly right. It's actually scaling. It's not going a distance of 1 centimeter. It's actually going a distance, like a unit of 1 in our code means, so a unit of 4 in our code is actually 4 decimeters or 4 10-centimeter increments. So every 1 unit in our code really corresponds to 10 centimeters of movement, kind of as the default in this programming language and with the rover. Now later in the webinar, we'll look at how you can change that default, but that's kind of how things are defaulted to start.
Michelle, that's exactly what Melissa said in the chat. She said 4 means 4 centimeters. So, yes.
40 centimeters or 4 decimeters.
Sorry, she said 40. I said it wrong. Thank you.
No, you're good. You're good. And this is, remember, like, grew up in Canada, right? So I feel like I'm speaking my home language when I get to speak in all these metric units, right? So this is like a happy place for me, but then don't ask me how many feet are in a mile or any of that nonsense, right? So, yeah. So, okay, well, thank y'all for trying to kind of explore this with us in a digital way. Super interesting. Tony, where do you want to go next?
So I'm looking at this code, and I see these drive commands, and the first thing I want to do is I want to see, like, does anybody know, looking at this, I'm thinking, how could we code pretty easily from this a square, like a square path for Rover to follow?
Ooh. Like, and we don't necessarily need to use these 4 lines of code. Like, you could use any of these 4. You could add other lines of code. You could delete some of these, et cetera. But we've learned 4 different commands. How could you use these kinds of commands of forward, backward, left, right to actually code out a square? Yeah, that's an interesting question. So do you want us to, like, yeah, let's spend a minute with that. Like, think to yourself, how would you write code that codes out a square? And maybe share that in the chat. Don't feel like you need to type an entire line of code, right? Like, just kind of give us the idea of how you would do it. And then I think there's actually multiple ways you could do this, right, Tony? So let's see if some of those maybe come out. So take a minute or two to predict how could we maybe code out a square pattern and share that in the chat. Jessica, I think that's called creative. I like that. I like that. I can see some of the chat messages kind of pop up one at a time, but I can't see the whole chat, so I'm trying to stay with y'all. Tony, do you have some things to share?
We do. Looks like we have some good ideas. So we have some people telling us that we should go forward and then turn right 90 and then go forward, turn right 90, and continue. And then we also have somebody that's suggesting that we could even put a loop in and go forward and then right 90. So, and I'm wondering, I think either one of those would work.
Nice. And so either something like this where we have a forward and then a left, and we kind of, I'm just copying that, and we repeat it a certain number of times or whatnot, right? Or when
so
we
Michelle,
repeat.
how did you do that, copying? How would you do that on the handheld?
Yeah, good question. So you can actually use the Shift key over here on the handheld. I'm doing that on the computer as well, but the Shift key on the handheld works the same way. And then using my touchpad, I'm kind of arrowing across to highlight what I'd like to copy. Then I can Control-C, just like to copy on a computer. And then I can also move to where I want to go and Control-V to paste it in. So I love that those same shortcuts that I use all the time on the computer work on the Nspire handheld as well. Neat. So, and then some of y'all had said, like, maybe we could loop this. There's all kinds of computer science that this goes into that we could delve deeper into as well. Like when you're doing something again and again, there are some different structures called loops that allow you to do things repetitively more efficiently or whatnot. But we could also code it out line by line as well, so different options. Ellen, that's a great question about. Go ahead.
Well, I was just wondering, it was so easy to do this square. Now it's got me thinking about an equilateral triangle path or a regular pentagon, a regular hexagon, or what if we wanted to generalize this to a regular n-gon?
Ooh. Yeah, that's interesting. Like the equilateral triangle might be a good next step. And I know that when you've challenged me to do that before, Tony, my first few iterations of that did not come out looking like an equilateral triangle. So they didn't even make a polygon. So we'll just kind of like plant that seed, but have you think about how we could extrapolate the ideas we've looked at here, just of these initial 5 commands, right? Connecting, and then also forward, back, left, right, and think about all the geometry that you could kind of go into with this to get started. Yeah. Tony, other things to add with that?
No, somebody said in the chat that they also did something similar, but they used XY commands, and I think we're going to talk about that. So.
Nice, nice. This is a perfect segue. Thank y'all. Okay, so yeah, I think that is where we're going next. So we've looked at these 4 drive commands, forward, back, left, right, but there's others. So I'm going to delete what we've got so far, except for our Connect RV, because my programs do not run well when I don't have that, right? And we're going to look at another command called 2XY. So I'm going to go grab it. It's going to be menu, go through the hub to the rover, and we're going to do another drive command. We've already looked at forward, backward, left, right, but this time we're going to go down to this other command called 2XY. So I'm going to insert that, and I'll just let you know that it needs 2 pieces of information in order to run. So I'll set it up with a 3 and a 4, but we'll actually look at what this does in a minute. I'm going to insert another command we haven't used yet. I'm actually going to insert, oops, not from there. I'm going to insert a command that will just pause the rover for a second. So I'm going to use a text command and have it say pause. And the only reason I'm putting this in is so that we can know for sure when this command is done, right? Like, oh, that just happened and now that's done. And because this pause command will actually, the text command will pause the rover until you push a button to exit out of the text box that pops up. So I'm going to kind of put that in. And then I'm going to go ahead and go through the hub to the rover, another 2XY command. And this time I'm going to have 2 values of maybe 0 and 0. So we're going to have 2 of these 2XY commands separated by this little pause function, so we'll know which one's which and kind of what happens. So this is the next code we're going to kind of think about. And again, I invite you to predict what would rover's path look like. But first, we need to talk about how rover is set up here. Oh, don't loop on me like that. We were just talking about loops, and now rover's getting, yeah, it's funny. Okay, here we go. So this is what our command looks like, or a code looks like, but there's a little bit we need to know about how the 2XY command works. So when we're going to use this command, we want to start by orienting rover to be set up kind of centered at the origin. So there's actually a pen well right here, and the pen, when it goes down to the paper, would land right about where the origin is, kind of the midpoint of the axis, or the axle, the axle of these front two wheels. So right about here is where the rover is centered at the origin. And we want the rover to be facing towards the positive x-axis. This is the front of the rover. So this is how we're going to set up the rover when we run this program in just a second. And so I invite you to predict and maybe share in the chat, like, what's going to happen, what path is the rover going to kind of trace out when we run this program. You might have a pretty good guess about where it's going, but how is it going to get there? So take a minute or two and share some of your predictions in the chat about what rover's motion is going to look like when we run this program. And again, y'all, this is like rough draft thinking. Like if we haven't put our hands on a rover before, we've never tried this before, we don't really know, right? We're just sharing some of maybe it does this or maybe it does that. Great, that's exactly what we're looking for, just some potential ways that this command might work and that rover might travel.
So Michelle, I'm seeing some people put some things that I also was thinking, and that is, I don't know if it's going to go rise over run, or if it's going to go 3 units to the right, 4 units up, and then it's going to come back to the origin. Someone suggested maybe a straight line to 3, 4, and then back, a right triangle. So we have a lot of suggestions, and all of those went through my mind as well.
Nice. And so this is exactly what we do when we're trying to make sense of how these lines of code work. When we're new to these, we try some things out, and then we run it, and then we see what happens. So we're trying to, again, kind of mirror that in this digital environment. So again, this is how rover's going to be set up. And then let's watch a short video clip to see what actually happens, to see if that confirms our predictions or has us refine our predictions. So again, I'm going to show the video here in the slides presentation, but Mike will drop a link. Oops, Mike will drop a link in the chat as well where you can watch it there too. So see it paused. Tony reaches in and unpauses it. Interesting. I'm going to play that again.
Wow.
So here's Tony kind of starting that. It's running the first 2xy command. Pauses. Tony unpauses it. It's running the second 2xy command. So share some of your thoughts on that in the chat about, like, does that confirm your prediction? Does it make you go kind of another way? Like, what are your thoughts about how that works? Share some of your thinking on that.
And while they're doing that, Michelle, I'll tell you, the first time I did this with kids, I think the kids were thinking like I did, that this was going to go over to 3 and then go up to 4. It was going to graph the way that we graph points. And when that rover turned and went straight to 3, 4, they were like, it's so smart.
Yes.
That opened up a whole new world.
Yes. And there's some really interesting mathematics going on under there, right? Like that it doesn't, I'm with you, but that's kind of how I graph, over 3, up 4. But Rover is doing some trigonometry underneath the hood, right, to figure out, okay, what angle do I need to turn to exactly to be facing that point, and how far do I have to go exactly, right, to get to that point that's 3 over and 4 down. It's also interesting because I saw some people talking about, like, but wait, like, when you did 0, 0, why didn't it stay put? Like, how did it know to go back? And so that's kind of an interesting thing to think about too, and this ties to how this is all coded under the hood as well. When this send connect RV line of code is sent, then wherever Rover is at that moment is taken to be the origin, and whatever direction it's facing is taken to be the positive x-axis. So it kind of like locks down, quote unquote, the location of the origin. And that's why we want to position the rover to be at the origin and facing to the positive x-axis when we run programs with 2xy, because it kind of sets that position in Rover's memory, and then you can use all these different 2xy commands and tell it to go all over this coordinate plane, and it will remember exactly where it is in relation to that origin that it started at. Is that a fair way to say that, Tony? What would you kind of add to that?
Yes, and I'm wondering, Michelle, if we put another send connect command in that code, I wonder if we could start a new origin from somewhere else, because that would open up a whole new world of things that I could do within the same program.
Yes, absolutely. And that reminds me of some like pre-cal kind of vector questions, you know what I mean, where sometimes when you're adding these two vectors and all that kind of stuff, so we can absolutely end up in that space. And that is something we can do, add another second send connect command to reorient, reorigin, do you know what I mean? Like set a new origin in that current location. So awesome. Mm-hmm. Great questions, y'all. This is awesome. So that's a little bit about, a little bit of sense making about how this 2xy command kind of works. And yeah, I think that's awesome. So Tony, anything to add to that before we, I thought somebody said polar coordinates. Did that happen?
Yes, I think they were talking about it following polar coordinates, the rover, to get to that point. Yeah.
Interesting. Yeah. And so we're not going to specifically look at that tonight, but you may have noticed that earlier in the drive commands that you can actually, instead of doing to XY rectangular coordinates, you could also have rover navigate by polar coordinates. So super fascinating applications you could do with that, kind of at that, what's a pre-cal standard here in Texas. So interesting. Okay, so now we're going to go kind of stay in rectangular coordinates right now, which kind of show up in about 5th grade through 5th grade through middle school here in Texas, as well as obviously throughout the high school. And we're going to look at a particular challenge / activity or application. So in this particular application, we're going to start rover at the origin, facing towards the positive x-axis. And our task is to write in code, and we're going to be using the 2xy command, and to get the rover to start here, somehow circumnavigate these 3 blue dots. So we have to do a path that somehow goes around those 3 blue dots, then somehow ends up over here so that we can push this orange cone up to that red dot. So again, this is a great task to give kids to work on, and we're kind of replicating that for you live in this webinar setup as well. So we want to kind of somehow tell rover to kind of move around those blue dots, end up over here, and push that cone over to the red dot. And like first, as a group, we can acknowledge there's an infinite number of ways that we could do this, right? That we could kind of navigate this or whatnot. But first, I think, Tony, you're going to give us some specific, like a specific path to think about. Is that right?
Yes. And before I do that, Michelle, I just wanted to remind you and me, Melinda asked about our graph paper, the type of graph paper that we're using, and I did tell everybody in the chat that we are going to address that at some point. I don't know if you want to talk about it right now.
Good question. Yeah, so this is actually, so Tony made this graph paper, and it is just 10-centimeter increments that she drew out by hand. But later in the webinar, we'll look at how you can use, you know how they have that sticky, like Post-it sticky chart paper that has the 1-inch grid already on it? Or you can actually buy a roll of 1-inch grid paper. There's a way we can change that default setting for the rover so that a default unit isn't 1 decimeter or 10 centimeters, but 1 inch. And so we'll look at that in the next activity as well. Is there more you want to add to that too, Tony?
No, that sounds great, and I think we're gonna look at that, right? So
yes, ma'am.
We'll talk about it more then. Okay, so I want to make sure that my rover does not hit those dots, and so I'm sitting at the origin facing the positive x-axis, and I think we ought to go probably to 4, 0.
Okay, I'm going to map out what you're saying, so we're going to go over to 4, 0.
Okay. And then 1, 2, that blue dot is at 2, 2. So how about 2, 5?
Okay, so I'm going to map that out as well, 2, 5.
Okay. And then that other blue dot looks like it's at -1, 1. So I'm going to say -4, 0.
Okay. Nice.
And then, let's see, that one's at -1, -2. How about -1, -5?
Okay, so way down below. Yep.
Okay. And now I've got to line up the rover so that it can push the cone towards that
yeah.
red dot. So I'm going to say 4, -3.
Nice.
And maybe that'll line up nicely so that when it heads toward the red dot, which looks like it's at -2, +3, yes, thank you, that should push my cone up through there.
Nice. And this is like what you just talked through, Tony, is exactly the process that kids kind of go through to map this out themselves, and that kind of problem solving about like, ooh, we could go here, here, here. Would these coordinate work? What are all these coordinates? So there's lots of kind of interesting work that we can do with that. So yeah, so let's imagine we're going to take that path that Tony just explained to us and actually kind of code that out. So I'm going to kind of downsize my Nspire software here for just a second. I'm going to try to, oh, bother. No, really, I want to. Let me do it this way. Move it up a little bit, but not all the way. So that we can kind of have a side-by-side here of the Nspire software and a picture of what we were looking at there with Tony's kind of path. And so then we would kind of think about like how would we actually code this out just using the 2xy command. So we wouldn't probably start by going to 3, 4. We were at the origin. Our first line of code would be like 2xy, what would that be, 4, 0? Does that look right?
Mm-hmm.
And then our next line of code, and again, feel free to share in the chat kind of as we're going through this live, but I'm going to go hub. Oops, I shouldn't have gone that way. Hub to rover, drive rover, insert another 2xy command. You went to 4, 0. We want to go to 2, 5, so 2 space 5. Okay. Y'all looked at copying and pasting earlier, so we could do that again. Copy these lines of code down, and then kind of finish out this particular code or whatnot to go to all these different points. Tony, anything to share on that while I'm kind of fixing those up? -4, 0, -1.
I think that looks good. And just to talk about the copy paste, you did Shift and the arrow key to highlight.
Yes,
and then just Control C and Control V to copy and paste, which is nice.
Nice. Yeah, absolutely. Yes. So 4, -3, and then we said this was a -2, +3. So we think this code might direct the rover along that path, like that's a potential program for that or whatnot. Okay. Let's watch a video. I think Mike did a spoiler alert on us, and may have shared this one already in the chat. That's good. He is like on the ball, moving us along, which is great.
I'm just ahead of the ball. I'm ahead of the ball.
Yes, yes. He's like, it was 7:34, which was the exact moment you should have been showing that video. So thank you for sharing that, Mike. I love when that rover spins around there, Tony, how you missed the cone, like missed just hitting it or whatnot. So
yeah,
here we have, yeah, right? And so here we have Tony's path. I also love how your coordinate grid wasn't quite big enough, so you just added to it in all the different directions. Super cool. Love it. So let's see what happens. And I think you made this paper cone, right? Like you just made it out of paper yourself. It's super cute.
I did, which my rover pushed that paper cone and halfway ran over it, but it pushed it to that red dot. So maybe if it had been made out of plastic, it might would have handled it a little bit better, but that was my homemade paper cone. So
nice, nice. And then we were talking earlier, too, about how you're like, well, I didn't really minimize anything. Like, this isn't necessarily the shortest path that rover could have taken, right, to navigate those points and then move the cone from its current position, kind of runs over a little bit. That's okay. It still counts and ends up on that red tape or whatnot. But there's lots of other neat mathematics we could do to kind of troubleshoot this further or refine it further, et cetera. So anything to add on that, Tony, before we kind of step out of this activity?
No, the only thing I'm thinking about is I'm thinking that, you know, with the send connect RV command and the drive commands that we've looked at so far, and the 2XY, and then we briefly talked about the polar, I'm thinking that just knowing those commands, there's a lot of different things that I can do. There's a lot of different coding and math that I can do just knowing that handful of maybe 4 or 5 commands.
Yes, I like that. That's actually a perfect segue into our next question for everyone to think about is like, what other math ideas or topics are you thinking about, or could we explore using the rover skills we have developed so far? And yeah, Tony did a great job of summarizing those: left, right, forward, backward, 2XY, maybe 2 polar. So take a minute and share in the chat, like, what are some other things you're like, ooh, I wonder if we could explore this idea, right? Or we could use rover to do this or whatnot. So take a minute or two and share some of those in the chat in light of what we've looked at so far.
So, Michelle, while we're waiting on some ideas in the chat, I was just wondering, you know, we could specify exactly, you know, how many legs or how many sides to the polygon that we want to create, using our 2XY. If we want to make sure that we hit all, you know, 4 quadrants, or how big or how large we want to make that.
Yeah, and then what you said just made me think too about we could like do some kind of drawing on paper, but then have then either code it out with 2XY or actually do a scale version of it using rover, right? How would you scale those distances? What would your angles be in order to map it out using forward, backward, left, right, you know? So that's interesting.
Yeah.
And I think someone said something about writing equations too, which is interesting kind of next step. Are there other things from the chat you want to pull out, Tony? I just see some of them popping up from time to time.
Sorry about that. Let's see. Yes, the linear equations and do simultaneous equations. Somebody mentioned there's an activity called Crash the Rovers that talks about that. Nice. And using real world problems to have rover map things out.
Awesome. Love it. Yeah, so y'all feel free to keep sharing in the chat some other things that you're wondering about, or like, oh, this makes me think of this or whatnot as well. And then we're gonna pivot and go to a different activity next called Corralling the Sheep, which kind of connects to some of what y'all were wondering about could we do something with equations and with writing equations and connecting that to rover as well. So for this one, I'm going to set us up with the context for this situation, and then we'll actually, I think we're going to look at this one on the 84, right, Tony?
Yes, that's a good idea, so we can see both platforms.
Yeah, okay, remind me about that in case I forget in a minute, get a little excited and jump right in. So here's how corralling the sheep works. Again, we're going to be on a coordinate plane, and we're going to have 3 precious sheep located at specific points on this coordinate grid. So Tony's kind of put those out there for us. And we have a specific task this time. And our task is to sketch a fence around the sheep that meets the following conditions. So we're going to fence in or corral these sheep. And our fencing has to begin at 0, 0. So it's going to start right here at the origin. It's going to have to be made of 4 linear functions with restricted domains. So there do have to be 4 of them. They have to be linear and they have to be functions. And then they're going to have just over a certain X domain, if you will. The 4 pieces of fencing need to be connected to form a polygon so that those sheep truly are corralled and cannot escape. and the fencing needs to end back up at 0, 0. So we're going to start at 0, 0. We're going to do 4 different sections of fence. Who knows where we'll go? And then we'll end up back at 0, 0 as well. And each of those fence pieces are going to be linear. So again, there's an infinite number of ways that we can do this. But in the interest of time, we're going to provide a fence layout, if you will, and then we'll think about how we might write the equations for that or whatnot. But with kids and doing this in professional learning face-to-face, we truly just kind of let everyone go at this point and see what they can kind of come up with. And then after we've done some of this math work in a minute, we're going to go over to Rover, and instead of coding out these lines, we're actually going to run a pre-coded program and then tell it the different values for our lines and see what happens. So Tony, I think let's move kind of quickly through what our lines would be. Do you know what I mean? Because I know we don't have a ton of time. How do you want to kind of do this one?
Okay, well, I've got some ideas here that I drew out on my paper, and I can give you what those points are. So my objective, I'm assuming that I have an infinite amount of fencing, and I'm not worried about that. I'm just worried about my sheep and not running over any of my sheep with my rover, if that's okay.
That's good. That's a good thing to worry about. I like it.
So if I'm going to start at the origin and I need 4 pieces and they all need to be functions, I would probably do the first piece. I would go over to 5, 0.
Okay, so something like this.
Yeah. And then I was thinking I would go up to 4, 4.
Up to 4, 4, so somewhere up here. Okay.
Right. And I chose that because I really wanted to go straight up, but I know it has to be a function, so I couldn't do that. So I just went to 4, 4. And same thing, I think I'm going to cut across to -1, 4 because those are also easy lines to find.
Those are very strategic lines, but yes.
Yeah, and then I'm going to cut down to 0, 0. And I did the same thing with -1, 4 because I really wanted to stop at 0, 4, but I realized that wasn't a function, so I couldn't do that.
So good, so good. Yeah, I like that. Awesome. So there's like a potential path, and I'm sure the symmetry of your fencing makes you happy, right? Like the fact that that was a parallelogram, like is a nice, yeah, that's a nice fit for your life, right? Like you're happy about that. So that's good. That's good. That'll totally work. So here's what we're going to do next. So let's imagine that this is the path we're doing, this path that Tony kind of suggested to us. And I'd like us to, we can kind of do this collaboratively as a team, but we need to write down what are the actual equations in y equals mx plus b form. So we need to change out this b, and we need to change, darn it, no, stop. Change out this m to other values for each of these 4 equations, and we'll kind of want to do them in order. So like what would the equation of this line be? What would its domain be? What would the equation of this line be? What would its domain be, etc. So maybe take a minute, pick one of these 4 lines, and then in the chat, can you share that out? Like line 1, colon, share its equation, share its domain. No real rush, but if we divide up these 4 and kind of share them out, then we can kind of knock these out, what we think the equations of these 4 lines would be. And I'll just get templates ready for all these so that after y'all share them out, I'm like ready to enter them. And don't feel like you have to do all 4. Just kind of grab one, kind of share it. Maybe you move to another one. Oh, Tony, great job. Tony jumped on the first one. How funny. Tony shared y equals 0, and you had a domain of 0 is less than or equal to x is less than or equal to 5. Okay.
Yes.
Okay. And then, Tony, remember, I can't really see the chat, so share with me any others so I can kind of fill them in, and that way we can also check each other's work, see if it's what we got.
Okay, so the second one is up, and it's y equals -4x plus 20, and the domain is from 4 to 5.
That's fascinating that someone jumped on line 2 so fast, because that one's like the hardest one for me to kind of reason through or whatnot compared to some of the others. So good job. And then see if someone seconds that or whatnot, if that looks right.
Yes.
Are there
and
others?
then we have the third one, y equals 4, and that goes from -1 to 4.
From -1 over to 4, okay.
And then we do have the last one, y equals -4x
Okay.
And it goes from -1 to 0.
Awesome.
And I think I've had a couple of each of those. So I think those are correct. We've had
like they've been seconded. Awesome. Yes. And so maybe y'all are like, okay, now I appreciate why Tony picked this line, like y = 0 or y = 4, right? But then also when you're doing this with kids, you might have a rule like no horizontal or vertical lines. Well, you first of all can't have vertical because it wouldn't be a function, but no horizontal lines, so that every time they have to kind of attend to a non-zero slope or a, do you know what I'm saying? So that's kind of interesting to think about. Neat. Okay, so we've got these lines, we've got our fencing. Now for the rover part, and we're going to jump over to 84 on this version. So instead of coding this one out, this is a pre-created program. The program in both 84 version and Nspire version is in the files that Mike's going to share with you sometime in the next 10 minutes. So we're going to go into the program menu here, and we're going to run this program called Linear. So I'm just going to go ahead and execute it, run it. It's already written for us. I'll push enter, and then we'll watch what happens. Boom, it asks us, what's the first slope? So I think our first slope was 0. Wasn't our first line y = 0, right?
Yes.
So slope of 0 and a y-intercept of 0 for that first line. And then it's asking us for the domain, specifically the min value. I think, Tony, you told me that one went from 0 to 5. Now it's asking me for my max x value, right? So it's asking us for the 4 pieces of information. Tell me what this line is, and then tell me what the restricted domain should be. So I'm going to push enter, and then if you could see my rover, right now it would actually be tracking this out. It would be drawing out the line y = 0, x + 0, or y = 0 from 0 to x is 0 to x is 5. It's going to stop after that. Yes, ma'am.
Okay, I just want to make sure. So in this program, because I know we changed platforms, so this program up there at the top called Linear, we didn't do any of this program. You just actually executed the program. It was already pre-written.
Correct. Okay. Yes. And the spoiler alert is that Tony and I actually wrote this program at one point, not in one sitting, but over a couple days in order to do this. But it's written in a very different way that this time you're not having to code all this out. It's pre-written, and you just interact with the code and provide it your mathematical your mathematics, so it will actually code it out. I mean, make the rover draw out the path for you. Is that a good way to explain that, Tony?
Yes.
Okay. So so now we would give it the second equation. I know this is tough to kind of see because you're not seeing the rover movement with it, but we have a video in just a second. So now say I'm entering the second line. I think you also said the second line had a slope of -4, a y-intercept of 20, and it maybe went from x = 4 to x = 5. Is that right?
Yes.
Okay. So we'll push enter. Then right now the rover would be doing that motion. It would map that function out for that restricted domain, ask for the slope of the next one. So I'm going to totally cheat here, y'all, and just put in like 1, enter 1. These are not the right things. I'm just moving through this part, do you know what I mean? So I can kind of get out of that program as if we did that all correctly. But we could have done it all 4 that y'all kind of gave me, right? I want to jump us back over into the slide deck for a second because I want to show you what this actually looks like when we run it. And I think Mike is about to drop a link for y'all, but I'll play the video here as well. This is a video Tony took of this exact process, and then I sped it up to 2 times motion. So this is twice as fast as real life video, only so that it would only take 30 seconds instead of 60 seconds for us to watch it live. But see how she's entering, oh, there's my slope. There's my y-intercept, there's my x-min, there's my x-max, and it's like, boom, draws it out for you. Enters her next slope, y-intercept, x-min, x-max, and then it draws that part out for you as well. So questions or comments about this activity? Again, we're not engaging with the code underneath the hood. It's a pre-written program where you are just feeding the program the slope, the y-intercept, the x-min, the x-max, and then it's going to actually trace that all out for you on a coordinate grid to allow you to test to see if your equations are correct and if you're really able to corral the sheep.
And no sheep were harmed in that video.
Which is not true for all of our rover videos, but in this particular set, no sheep were harmed. That's true. That's true.
Michelle,
okay, so,
I think this would be a really good time to address the grid and talking about, like, well, what if I didn't have this 10 centimeter and I didn't feel like making this for 5 different groups in my classroom, and I have the 1-inch poster paper.
Yes. So let's look at that super quick because we have 2 minutes left before we have to pass back to Mike. So let's answer that question. So I'm going to clear this out. I'm going to go into the program, and I'm going to go into edit. So I'm kind of going under the hood here for a second. And you can look at the program on either calculator to see how did we actually code this out. But what we want to do for right now is I'm going to actually insert a line. I'll do alpha F5 to insert a line above on the 84. And then within the programming menu, I can go to Program, Hub, Rover. That should feel the same, even though it looks a little different on the 84 platform, but through the hub to the rover. And then when you go down to rover setup, there's a command both on the 84 and on the Nspire of this rover grid meters per unit. And what we can do here is we can say, well, how many meters do we want there to be per unit of rover? We can use a really nice number like 0, oh, crud. This is my life, y'all. Sorry, like that note, that never happens to anyone else, right? Like that's just me. Sorry, I'm adding in quotes, sorry, closing the parentheses. So we can use a unit of every 0.0254 meters is a unit, and that will set it to where every inch, right? Because every 2.54 centimeters is an inch.
Right.
That will orient our grid to be based on inches. So I'm going to show you a picture of what that looks like when we ran that same program with those same lines, but on an inch grid. You can kind of see this is the 1, 2, 3, 4, 5, and this is what the output of that program looked like for those itty-bitty sheep, that itty-bitty corral.
I might need smaller sheep, or I might want to change the coordinates. Those were the same coordinates that we used on the big graph paper, but we might want to change the coordinates of the sheep and maybe use smaller sheep. I have one more thing, Michelle, that I'd like to get in before we pass it to Mike. And would you address the fact that I noticed, like, the 2 activities that we did choose to look at tonight, the first one involved some basic coding that comes in handy that we could use for all kinds of things. We even talked about polar coordinates, geometry, and so forth with those 5 commands that we learned. But then the second activity that we looked at didn't involve coding, but it involved a lot of mathematics because we were finding the equations of the lines and so forth.
Yeah, I think that's a good summary, that the rover, we can code things out, kind of like we did on the Nspire platform, and explore mathematics that way. But there's also value in having these pre-created programs like we did with the linear, that we don't do any of the coding ourselves on, but then we interact with them by running them and giving them mathematical inputs to do things with as well. So as we wrap up, we just wanted to let you know that there's a number of summer workshops happening across the United States this summer. I'll go ahead and drop that link in the chat while I stop sharing to turn it back over to Mike. But there's a number of sessions specifically about this idea of leveraging the Innovator Rover in the service of mathematics teaching and learning.
I got all 6 of them in that list that you just showed, Michelle, just on the Math Innovator Rover this summer.
Yes, 6. I think that's right. Yeah. So, Mike, I know we cut into your time. Thanks for being gracious with us. I'm going to go ahead and mute for a second and let you wrap up for us tonight.
Thanks so much. One thing I wanted to mention, I had a few people that were curious about learning more about the TI-Innovator CE. And let me just share on our website where you can get a little more information. Under professional development, if you slide down under webinars, like we're on one tonight, you can view the on-demand webinar library. And if you specifically look at, say, the TI-84 plus CE, these are all the webinars that have been archived on the 84 CE. and the one near the bottom says Introduction to the TI-84 Plus CE, so you can expand that and check that out. Our speakers were Michelle and Tony. So you can watch the video from that webinar and also download all the documents from that webinar. Also, if you're looking for maybe this webinar, you're hoping for more like step-by-step or hands-on kind of coding experience. One way to do that, besides attending a T-Cube Summer Workshop or a regional summit, is under the Resources tab, under the Activities tab. You can go to TI Codes, and this is a great place to really go at your own pace. For what's worth, this is how I started learning how to code on TI technology. It allows me to sort of make mistakes and go back and try things. So I highly suggest checking out the TI Codes 10 Minutes of Code website available on our website, education.ti.com. Again, you can use this for the TI-84 Plus CE or the TI-Nspire technology family. So Michelle already gave a great plug for the T-Cube Summer Workshop, and we mentioned that tonight there's one lucky winner that's going to be getting a free registration to a T-Cube Summer Workshop, and tonight's lucky winner is James Zuber. So James, congratulations. We'll be in touch over email in the next couple of days to give you a little more information, but we hope to see you as well as everyone else at a T-Cube Summer Workshop. To receive a certificate of attendance, go ahead and click the link in the chat window. Also promise the link for the documents that were used tonight by Michelle and Tony. If these aren't working for you for any reason, hang tight. You'll automatically get a follow-up email in a couple days, and that follow-up email will be links to the recording, the certificate, and the documents. And if you're watching this on demand, go ahead and copy this link into your favorite browser to receive your certificate. So thanks so much, Michelle and Tony, for everything you shared tonight. Really appreciate it.
Thanks, Mike.
Thank you.
And thanks, everyone, for joining us. We hope to see you back online real soon. Have a great night.